Okay, so today we're going to continue with section 3.1, or roughly section 3.1, which is on direct proofs. This is how you prove a conditional statement. If P then Q, you assume that P is true, then you do some magic to deduce that Q is true, and inside that magic needs to be only stuff that you know to be true. So that's definitions, axioms, and any previous results. Okay, so we spent last time, we went over the axioms of the real numbers, axioms of equality, and then we proved two nice theorems, right? One says that if you have an equality of real numbers, you can add or multiply the same thing to both sides and retain equality. And the second theorem, which we're going to call the cancellation law, says that sort of the converse of that is true for addition. So if A plus C equals B plus C, then you can cancel the C's and conclude that A equals B. So this is all the things that we know about the real numbers so far. Let's get a new theorem, which will also illustrate a new technique, which is the following. The additive identity is unique. What I mean by this, it means there is only one real number with the property that A plus 0 equals A for all real numbers A. Right. So if you go back and look at the axioms, what we did is we assumed that there was an additive identity. We assumed that there's some real number which we called 0, such that A plus 0 equals A no matter what A is. But just by these axioms, this doesn't rule out that there might be more than one number with this property. But this theorem says that if you just assume these axioms about the real numbers, you actually automatically know that there's only one additive identity. So what's the technique here? How do you prove that something is unique? So in order to prove something is unique, the technique here is suppose that you have two. So suppose that you have two of that thing, whatever the thing you're trying to prove is unique is, say X and Y, then prove that X equals Y. So what we'll do is we'll suppose that we have two additive identities, two things that behave just like the additive identity, and then we'll show actually they have to be equal to one another, which means that actually there's only one additive identity. Those two things that we took at the beginning were actually the same. Okay, so let's get this proof. So let's suppose, so we're already assuming that there's an additive identity in the real numbers, which we call 0. So suppose we have another one. So let's suppose that 0 prime is also an additive identity of R. Right, what does that mean? That means for all real numbers R, so for all A and R, rather, A plus 0 prime equals A. That's what it means to be the additive identity. Okay, so there's many ways to do this, but also, so what we can do is we could just pick any A like this, any real number you want. Okay, but also, since 0 is the additive identity, for any A, for the same A plus 0 equals A as well, right? Because 0 prime and 0 are both the additive identity. Let me just check to make sure which order I wrote this axiom in. Yeah, okay. Now what do we have? We have that this is equal to A and this is equal to A. Well, what do you want to use? I would like to use transitivity of equality, but technically we can't use transitivity of equality, right? What does transitivity of equality say? Transitivity of equality says that if x equals y and y equals z, then x equals z, right? This is just in parentheses for our own knowledge. Here it's like we have x equals y and z equals y. So really what we should do is we should use commutativity to flip around one of these things. So now by commutativity, sorry, this is not commutativity. Here I would like to flip these things. This is actually not commutativity, I misspoke. This is by the symmetry property of equality, right? I'm not commuting an addition, I'm flipping around an equality. So by symmetry of equality, we know that a equals a plus 0. And now I can use transitivity because this is equal to this. So now by transitivity, a plus 0 prime equals a plus 0. Okay, now I would like to use cancellation, but cancellation technically only told us that if we added something on the right, then you could cancel it. So I guess technically I should commute these things. So by commutativity of addition, we have that 0 prime plus a equals 0 plus a. And so finally, by the cancellation theorem, we have that 0 prime equals 0 because we can cancel the a's from both sides. And maybe I'll say as desired because that's what we want to show. Okay, so what do we learn? For one thing we learned is how to prove something is unique. This is a common technique that you'll use all throughout the rest of your mathematical career. To prove something is unique, you suppose that you have two things, so they're the same. Also, hopefully we saw another example of trying to be extremely careful with what axioms you're using or what results you're using and making sure that you can really use them. Okay, so one thing here is here I misspoke initially, right? Here I said commutativity when I meant symmetry, but I fixed myself. I corrected myself. I said the correct thing. And then here, even at the end, it seems like you'd want to use cancellation here, but technically the cancellation theorem we have doesn't apply because the cancellation theorem that we have, sorry, that's the wrong slide. The cancellation law or cancellation that we have only allows you to cancel on the right side. So I had to flip them around using commutativity. Okay, another thing we could have done is we could have just proved this theorem also to say that if c plus a equals c plus b, then a equals b. But I would have to prove it somewhere, right? So here's one proof that the additive identity is unique. Okay, but it turns out this is not the only proof. So here's an example where there's many ways to prove the same thing. So let's actually prove this again. Right? The good thing about mathematics is, one nice interesting thing about mathematics that people think that in mathematics there's like when you're taking it as an high schooler or an elementary schooler or whatever, you think, oh, the reason I like mathematics is there's one right answer and it's either right or wrong. But actually that's just like arithmetic, right? When you add two numbers, there is one right answer. But mathematics is really about ideas and logic. And there's often more than one correct way to think about something, more than one line of reasoning that will get you to the same result. And you can learn something new by seeing a different proof of the same fact. Okay, so same setup as before. Let's suppose that 0 prime is another additive identity. Right? Again, by definition, this means that 0 prime plus a equals a for any real number a, right? any real number a plus 0 prime equals a. That's just the definition of being the additive identity. I'm just trying to remind the reader. All right, so now let's consider the sum 0 plus 0 prime. So I'm saying now consider this expression. Well, or you know what? Yeah. Well, by this property, this sum must equal 0 because it's something plus 0 prime. Right? So since 0 prime is an additive identity, let's say an additive identity because I don't know there's only one yet. 0 plus 0 prime equals 0. But also, by commutativity, 0 plus 0 prime equals 0 prime plus 0, which equals 0 which equals 0 prime since 0 is an additive identity. Right, so this sum, 0 plus 0 prime, right now it equals 0, and it also equals 0 prime. Okay, so now I would like to use transitivity. Technically, I can't because I would need to use symmetry of equality first. But from here on out, for the rest of the class, if you get A equals B and A equals C, I will allow you to use transitivity of equality to say that B equals C. Okay, because we've already sort of seen Y once, we've used symmetry once. Unless the problem is specifically to justify everything by the axioms, which will happen in this class, except in that situation, you don't need to use the symmetry first. Okay, but since we're doing this carefully here, let's do it totally carefully. So by symmetry of equality, let's say 0 equals 0 plus 0 prime. So by transitivity, zero, what am I doing? Yep, 0 equals 0 prime. Right, because now if you combine this with this using symmetry, you get that 0 equals 0 prime by transitivity. Okay, which is what we wanted. Okay, so there's another proof that additive identity is unique. Our first proof used sort of any real number A, and then you use the additive identity property of both 0 and 0 prime, and then transitivity. For this proof, basically, we added 0 to 0 prime and said, oh, that has to be 0, that also has to be 0 prime, therefore 0 and 0 prime are the same. Those are slightly different techniques. Okay, so on your homework, you'll have lots of problems like this. I mean, by lots, I mean probably I'll give you 1 or 2 for the next few weeks where you have to really carefully justify everything from the axioms just because it's a good idea to know why things are true. So these 2 results will be proved on problem sets. So to be proved even on problem set, maybe just your next one. So since you're going to prove them from the axioms, in lecture, I'll assume they're true. But you need to prove these from the axioms. So 1, for every real number A, A times 0 equals 0. Sorry, let me state this as written. 0 times a equals 0. Of course, since multiplication is commutative, it doesn't matter which order technically, but. And then 2 for every real number a, -1 times a equals negative a. Okay, and as I have said several times in this course, if your roommate, if you still have a roommate, walks in on you doing your Math 300 homework and they see that you're proving 0 times a equals 0, they're going to think that's something I've known forever. But it's not an obvious fact if you're just going from the axioms, right? What does this first one say? This first one says if you take the additive identity, which is defined by some sort of addition property, so you take the additive identity and then you multiply it by any number, you get the additive identity back. Right? Why should the additive identity have any property with respect to multiplication? It's not obvious at all. The second one says, take the additive inverse of 1, multiply it by a, and you'll get the additive inverse of a. So if you take the additive inverse of the multiplicative identity and you multiply it by a, you get the additive inverse of a. If you state it like that, it's not obvious why it's true, right? But I mean, we of course know that these things are true in the real numbers, so they seem very plausible because we're used to them. But there's sort of no reason to think, oh, the additive identity times anything should give you the additive identity. Why? So you will prove that from the axioms. Okay. But for now, since you'll prove it, I'll assume that they're true to prove the next result. So here's the next result. And I'll state it just like this. -1 times -1 equals 1. Again, it's hard to know. It's hard to look at this and not think that it's obvious. But what does this say? This says, take the multiplicative identity, take its additive inverse, multiply it by itself, you get the multiplicative identity. That, again, is not really an obvious fact, I don't think. If we're just working from the axioms, why is this true? Okay, so let's prove this. Okay, so since -1 is the additive inverse of 1, therefore, -1 plus 1 equals 0. That's what it means to be the additive inverse. Okay, so now what I'm going to do is I'm going to use the theorem that you're going to prove. Sorry, not yet. Not yet. Now what I'm going to use is I'm going to use what we called Theorem 38, which is I can take an equality and multiply by any real number and maintain equality. Okay, so now by Theorem 38, if I take this equality, I can take -1 plus 1 and multiply it by something, and that's going to be the same thing as 0 multiplied by something. Any number I want here, right? So I'm going to choose -1. Why am I choosing -1? I'm choosing -1 because I want to get -1 times -1. Okay, so I looked at this theorem. This theorem is about the additive inverse of 1. It's about -1. So I wrote down the definition of being -1. And then I want to multiply by -1 somewhere. So I use Theorem 38 to do it. Okay, so what I'm trying to say is these steps aren't any kind of magic. If you try different things, eventually you'll try this. Right? You only know so many things about the real numbers. You only have so many axioms. The first thing to do is just try something. So I want to prove this thing. First thing I'll do is I'll write down the definition of the additive identity. Sorry, the additive inverse of 1. And then I want to multiply by -1. I basically only have Theorem 38 in order to do that. Okay, so now I can use the result of this homework exercise, which will prove, which is that 0 times anything equals 0. Right, so by the yet to be proven homework exercise, which you will prove, -0 times -1 equals 0. So this means that -1 plus 1 times -1 equals 0. Okay, now we can use distributivity. That's natural enough. So by distributivity says that I can distribute this multiplication over this addition. So -1 times -1 plus 1 times -1 equals 0. Okay, now 1 is the multiplicative identity. So 1 times anything is that thing. In particular, 1 times -1 is just -1. Since 1 is the multiplicative identity, 1 times -1 equals -1. So -1 times -1 plus -1 equals 0. Finally, what do you want to do? You would like to well, okay, there's several ways you could proceed. I'm going to proceed in one way, but I can imagine you doing things another way. Okay, so one thing that you can do here is you can add 1 to both sides using theorem 38. You can reassociate using associativity. You can use, right, so here's one track that I'm not going to go down, but you could write it up this way. What you could do is you could add 1 to both sides, right? Use the additive identity property to make this one. You could reassociate this addition. After you reassociate this addition, you can use the fact that this is the additive identity to get 0. Sorry, the additive inverse to get 0. And you can use that this is the additive identity to get the thing that you want. That's one way to do it, right? Let me do it a slightly different way. So let me leave this as this here. One thing that you could do is you could add 1 to both sides using theorem 38. But what I'll do is I'll instead rewrite 0 as something else. So we already know that 1 plus -1 equals 0. So again, since -1 is the additive inverse of 1, 1 plus -1 equals 0. So by transitivity, or by substitution, let's say by substitution actually. Whoops. All right, so look here, 0 is equal to this, so I can plug it into this equation. By substitution, -1 times -1 plus -1 equals 1 plus -1. I just substituted in that different expression for 0. And now what's nice is I can use the cancellation law. Right? So the cancellation law allows me to cancel these two things. So now by the cancellation law, -1 times -1 equals 1. So if you multiply the additive inverse of the multiplicative identity by itself, you get the multiplicative identity. So I mean, it's kind of amazing that this multiplication follows just from the axioms we laid down. I don't have to assume this. If I just assume some properties of addition and multiplication, this always has to happen. So in fact, this happens in any field. Okay, but as I said, this happens in any field. Let's go back to some question I was asking last time, which is once we have these 7 axioms, it doesn't uniquely identify the real numbers because also the rational numbers satisfy all these axioms. And there are other fields that also satisfy these axioms. So we need to assume some more things about the real numbers in order to get the real numbers. To be honest, we're actually not even going to get all the way to the real numbers in this class. You'll have to wait for real analysis I think in Math 327, or maybe in the 400 level real analysis class. But one thing that we have not yet made any axioms about is we haven't made any notion of the fact that the real numbers have an order. Right? Here's all the things I assume about the real numbers. I haven't said anything like, oh, 0 is less than 1. So we're now going to introduce some more axioms, which I'll call the order axioms. The real numbers have an order to them. We'll introduce this order by using the order axioms. Okay, so what we're going to do is we will assume that some real numbers are just what we're going to call positive. Okay, so I don't even know what a positive number is. I don't know that 3 is positive and -4 is not positive, but I'm just going to assume that some real numbers are positive. Okay, so let's call the set of positive reals let's call it R plus. So right now I don't know any numbers that are positive. All I'm saying is that there are some real numbers that I'm going to call positive. Okay, so similarly, let's assume that we have some positive integers and positive rational numbers. Okay, so now I'm going to make some assumptions, some axioms. Okay, so axiom 12 is called positive closure. So if A and B are positive real numbers, then A plus B is positive and A times B is positive. So I'm going to assume that the positive numbers, whatever they are closed under addition and multiplication. Okay, and the next order axiom is called trichotomy, or the trichotomy law, which is this: if A is a real number, then exactly one of the following is true. Okay, so either A is positive, in other words, A is an R plus, or negative A is positive, its additive inverse is positive, or A equals 0, which says that 0 is not positive, right? Because exactly one of these situations happens. If A is 0, we just call it 0. Otherwise, we know that either A is positive or its additive inverse is positive. Okay, and I think it's very surprising that actually just these two laws, just these two axioms, capture the notions of positivity and negativity and order in the real numbers. All I'm assuming is that we have some positive numbers that are closed under addition and multiplication, and that basically every number or its additive inverse is positive. But just from these, it's like, okay, well, between 3 and -3, one of them is positive, one of them is not positive. How do I know which one? It turns out that all the notions that you have of order of the real numbers are captured just by these two axioms, and we'll develop some of them in class and on problem sets. Okay, but since we now have this notion of order, or positive numbers rather, I can make a new definition. Okay, so here's my new definition. It's actually several definitions. I'm going to define for real numbers A and B, let's say put it this way. So for real numbers A and B, I'm going to define this symbol, A less than B. What does this mean? I will define this to mean that B minus A is positive. So again, right now, I don't know any numbers that are positive yet, which means that I can't put any orders on any numbers yet. Right now, I don't know that 3 is greater than 2, or 2 is less than 3, because I don't know if 3 minus 2 is positive or not, but I will soon. Okay, I also just have to find this symbol. A less than or equal to B means A is less than B or A equals B, which is what you expect it to mean. But now that I've defined less than and equal and the word or, I know what this symbol means. And for those of you following along with LaTeX at home, this you get by \LEQ for less than or equal to. Okay, I'll also find the symbol greater than. So A greater than B means A minus B is positive. A greater than or equal to B means A is greater than B or A equals B. And then just for ease of referring to things, we say that A is negative if its inverse is positive. Okay, so I have given the axioms for the positive numbers, and this leads to the definition of the less than equal to, greater than, and greater than equal to signs. Okay, and while we're here talking about positive things, I want to introduce one more axiom here, but this axiom is actually not for the real numbers. This axiom is for sets of positive integers. So this is, I mean, it's sort of good that I have this on another slide because now I'm not assuming this for the real numbers. So this is called the well-ordering property. Okay, so let me just put in red this property, or let's say this axiom holds only for sets of positive integers. So here's the axiom. It's called 14. If you ever have a set of positive integers, you can use the well-ordering property on them. If S is a set of positive integers, then S has a minimum element. Okay, you may notice that I haven't defined what a minimum element is, so I should do that. So let's define this. Here's the definition. If S is a set of positive integers, then A in S is called a minimum element. If A is less than or equal to B for all B in S. So if you have an element that's less than or equal to every other element in your set, that's called a minimum element. Okay, and this morning I said this axiom is only true for sets of positive integers. So if you take the open interval 0, 1, this is a set of positive real numbers. Without a minimum element. Which is why I'm saying that this only holds for sets of positive integers, but it's the last axiom that we're going to use in this class, I'm pretty sure. Let me just check the sheet. Yeah, this is the last axiom in the class. And since we just defined positive things, I might as well add it here so we have our full set of axioms now. Okay, so now let's prove some results about positive things. So here's our first result. So a real number A is positive if and only if A is greater than 0. Okay, so this is actually just sort of immediate by definition. And in fact, I think I'll leave one direction of this as an exercise for you. Again, I don't know yet any numbers that are positive, but eventually, if I get that something is greater than 0, I'll say, oh, therefore it's positive, because by this theorem. Okay, just technically I need a new technique here, right? Because this is an if and only if statement. So to prove P if and only if Q, hopefully this isn't surprising, prove if P then Q and if Q then P. So if you want to prove a real number A is positive if and only if A is greater than 0, you prove if A is positive, then A is greater than 0. If A is greater than 0, then A is positive. Okay, and there's sort of a traditional way to notate this, which maybe you've even seen in your previous classes, which is you always want to give your reader some signposts, some directions about what you're doing. Therefore, they can follow and they won't get confused. So this statement here is like a statement, let's call this one P and this one Q. So really it's like you're trying to prove P if and only if Q. And first we'll prove if P then Q. And just to give some notation for our reader, at least in lecture, maybe on your exams, on your homework, I'll use this symbol to say I'm going to prove the forward direction. I'm going to prove if P then Q. Then later when I do the reverse direction, I'll use this symbol to say, oh, now I'm going to prove if Q then P. And this is like signposts for my reader. So my reader knows, oh, this is where the first half of the proof is, this is where the second half of the proof is, and if they've done both of these, they've proved the if and only if. Okay, and by the way, this symbol is called capital R right arrow. Okay, so let's prove this. So let's prove if P then Q. So let A be a real number. And suppose that A is positive. Well, what can we don't have that much, right? So let's go back here. What does it mean to be positive? Well, I want to prove that A is greater than 0. So from here, I need to prove that A minus 0 is positive. If I can prove that, then by the definition of A is greater than B, I'll have that A is greater than 0. Okay. So we note that since 0 is the additive identity, zero plus 0 equals 0. Right? But what does this mean? This means that 0 is its own additive inverse. Right? So, because this is something plus something equals 0, this means that these two things must be additive inverses. Have I proven that additive inverses are unique yet? Maybe not. Maybe I need to put this on the homework. Okay, so I need to put this on the homework. Okay, so by a problem set exercise, additive inverses are unique. So 0 equals negative 0, right? Because this means the additive inverse of 0, but 0 is also the additive inverse of 0, so therefore 0 equals negative 0. Okay, now hence, A minus 0, which is the notation for A plus negative 0, equals A plus 0, because negative 0 is the same thing as 0, which equals A. Because 0 is the additive identity. So A is positive, Therefore, a minus 0 is positive. That's by substitution. Since a is positive, by substitution, a minus 0 is positive. And now, by the definition of greater than, if a minus something is positive, that means that a is greater than something. So by the definition of greater than, we have a is greater than 0, which is what we wanted. Okay, and now to do the reverse, or to do the converse to the statement, you sort of just reverse these things. So I'll also leave this as an exercise. Okay, so try to prove this, try to write a nice clean proof of this fact. Okay, so I think just one more result for today. And what it will be is it will be our first positive number. So here's a theorem, 1 is positive. Again, it's kind of amazing that you can conclude that just from these two axioms, just the positives are closed and every number or its additive inverse is positive unless a number is 0. Why should these two things themselves say that the multiplicative identity is positive? Let's prove it. So this is going to use a new technique, which is called proof by contradiction. Okay, so in order to prove a theorem, you assume the theorem is false, and then you deduce a contradiction. Remember, a contradiction is a statement that's never true. So if you assume the theorem is false and you deduce a contradiction, that means that your assumption was wrong because it reached a contradiction. Therefore, since your assumption was wrong, the theorem is not false. So the theorem is true. So therefore, your assumption was wrong. So the theorem is true. So kind of a sophisticated technique here, proof by contradiction. You assume the thing is false, you reach some contradiction, therefore you conclude that it's true. And as with sort of everything in this class, you'll use this technique over and over and over again in your future math classes. So let's prove this, that 1 is positive. So suppose for contradiction that 1 is not positive. Again, you want to give your reader enough information about what you're doing. So it's really nice to say suppose for contradiction, so your reader knows, okay, I'm about to read a contradiction proof. So I'm going to assume that 1 is not positive, and I need to reach some kind of contradiction that will prove that 1 is positive. Okay, now by the trichotomy axiom, right, either 1 is positive, or negative 1 is positive, or 1 is equal to 0. So 1 is not positive, which means that either negative 1 is positive, or negative 1 equals 0. Sorry, or 1 equals 0, right? Either 1 is positive, or negative 1 is positive, or 1 equals 0. Okay, so let's break into cases. So case 1, suppose negative 1 is positive. I'm going to reach a contradiction. Okay, now by the closure of the positive numbers, negative 1 times negative 1 is positive. Because if you multiply two positive numbers together, you get a positive. But we also showed that -1 times -1 equals 1. 1 is positive. But I assumed that 1 was not positive, so this is a contradiction. So I've reached a contradiction in case 1. So now, case 2, suppose that 1 equals 0. But this actually immediately goes against an axiom, because in axiom 5, I assume that there are two different real numbers, 0 and 1. So I assume that the additive identity and the multiplicative identity were different numbers. So this actually contradicts axiom 5. Which part of it asserts that 1 and 0 are different real numbers. So no matter what, we've arrived at a contradiction. Therefore, our assumption must have been wrong. So it must be the case that 1 is actually positive. So in either case, we arrive at a contradiction. Therefore, 1 must be positive. Okay, so now we have a positive number. The multiplicative identity must be positive. Okay, so like I said, you'll have more problems where you'll have to go directly from the axioms, but you'll also have a bunch of problems from now on where you don't have to do everything directly from the axioms. So these 2 lectures sort of covered this axiomatic approach to real numbers. We're now going to jump into more stuff, and in the rest of the book, other than when I tell you prove directly from the axioms, we won't be so careful about doing things directly from the axioms. Okay, so you'll see what I'm talking about next time. We're going to talk about divisibility, which is basically starting in section 3.2 of your book.